Hello, everybody. Welcome to the third episode of Inside DFINITY. In this series, I take you inside the DFINITY Foundation's internal R&D processes by showing you clips from our weekly global R&D meeting, where people perform demos and provide updates on work that's ongoing. In this episode, I'm going to talk about, or rather show a clip pertaining to the extension of internet identity support to the Windows Hello authentication system. So I've chosen this clip. It's actually a few weeks old, and I'm sure, as most of you know, internet identity's been supporting Windows Hello for some time. But the reason I'm showing this clip today is that we've just passed 725,000 internet identity anchors created, and that's just an incredible figure. We only underwent Genesis 4 months ago, so it reflects just an extraordinary, tremendous growth. And as many of you know that follow the stats, we don't get much reportage from the paid crypto media, but in actual fact, not only is the internet computer the most interesting new blockchain technology, but it's also the fastest growing network in terms of the number of smart contracts running, the dapps running, developer growth, and active user growth. So we're laser focused on seeing that internet identity anchor count getting to 1 million. Hopefully we can make our first 1 million internet identity anchors within the first 6 months, and then go on from there into the billions eventually. So what is internet identity? Internet identity is a unique, anonymizing blockchain authentication system that allows users to authenticate themselves anonymously to dapps running on the internet computer network. Now, excuse my coffee, I've been going for a while. The internet computer is unique in a number of respects. It's the first public blockchain that can scale its capacity without bound, such that it can host on-chain any amount of computation and any amount of data, which means that you can use it to actually host things like social media as well as run more traditional applications like DeFi. It's the first blockchain to run at web speed. So it actually finalizes transactions that mutate state in 2 seconds, which compares to other fast blockchains very well. For example, Solana takes 16 seconds to finalize state. It can also process transactions that don't mutate state, or rather where the state mutations will be discarded, in milliseconds. And this has enabled us to allow smart contracts on the internet computer to actually serve interactive web content directly into users' browsers. It's the first blockchain ever to serve web, thus providing for end-to-end decentralization. So for those that aren't familiar, all of the other blockchains in the world support a very different model. They support what I call blockchain applications, not true dapps. So, when you create a dapp for Ethereum, say, you create a website on big tech's cloud, typically. So, you get an account on Amazon Web Services, and you upload a website to it, and that website interacts with a blockchain backend. It talks to patches you through to smart contracts, and the challenge with that, of course, is you haven't got full decentralization. So whoever's running that website is exposed to legal jeopardy, and that's why, for example, Uniswap probably had to delist half its tokens recently, and all these NFT websites are constantly getting DCMA takedown notices because the developers behind these systems, of course, have their names on the website. It's not really a dapp, it's a blockchain application. And you as a user, of course, also have to trust that the website isn't malicious. You have to trust that the whoever put that website up there is doing the right thing. You have to trust that it hasn't, the Amazon Web Services or Google, whatever it is, account hasn't been hacked. And you have to trust that the big tech cloud operator is also honest. You never really know that you're even interacting with smart contracts. With respect to the Ethereum ecosystem, these websites need to work in conjunction with a Chrome extension that you need to install in your browser called typically MetaMask. So, the internet computer solves for this legacy situation by enabling smart contracts, which, are able to scale their capacity without bound, run extraordinarily efficiently and extraordinarily fast by enabling those smart contracts to actually serve interactive web content directly into your browser without any need for intermediaries. And they do that securely. So smart contracts on the internet computer can make use of this thing called chain key cryptography. And the assets that are being served into your browser by HTTP responses actually come with chain key certifications that are validated by a service worker running in the browser to make sure they've not been tampered with. Now, okay, so you want to build some kind of a DEX or a social network dapp on the internet computer, and you're able to serve the interactive web content directly into the user's browsers without any intermediaries. Fantastic. But how do your users authenticate themselves to you? That's where internet identity comes in. Now, internet identity allows you to create any number of internet identity anchors. They're called IIs. You can actually maintain a bunch of them if you want. And to each II, you can assign any number of devices. So the devices have to support something called WebAuthn. And for example, that could be the fingerprint sensor on your laptop. It could be the Face ID system on your phone, or it could be a dedicated HSM device like a YubiKey or a Ledger hardware wallet. Now, let's just think about the fingerprint sensor on your laptop for a second. How does that work? Well, there's actually a chip inside your laptop that can hold public key pairs. And that chip is tamper-proof, so you can't open it up and get the keys out. What you have to do is pass transactions into that chip where they can be signed. Now, of course, you don't do that yourself. That's handled by the WebAuthn subsystem in your operating system. So what happens is that, let's say you go to, a dapp that's a DEX or a social network running off the internet computer. It's going to ask you to authenticate yourself. You're going to specify an II, an internet identity handle, and then you're going to have to show that you have one of the associated devices. So, for example, if you've associated the fingerprint sensor on your laptop, you're going to press the fingerprint sensor, and the biometric hardware subsystem will, validate it's one of your signatures and patch the transaction through and put it inside that special chip. It's called a TPM, where it'll sign the transaction, and it comes back out and creates a session that enables you to interact with the DEX or social network or whatever it is you've created on the internet computer. If you want, you can add multiple devices. So typically, let's say you've got an II you use with social media. Probably you're going to add your fingerprint sensor. You're also going to use Face ID. So, if you're on your laptop, use your fingerprint sensor. If you're on your phone, use your Face ID. If you want to, you can add some backup devices like YubiKeys and Ledgers. You can even add a seed phrase if you want to, but it's not necessary. Your access, your control over that II is mediated, if you like, by these hardware devices. It's that you're authenticating using these hardware devices that maintain public key pairs securely inside these tamper-proof chips. So, the great advance is that you can have an II and you can authenticate yourself using a range of devices that you've assigned to the II. And you never have to touch any cryptographic key material. You don't bother about seed phrases and things like that. So it's actually vastly more secure, as well as being far, far easier to use. And it doesn't require, a a Chrome plugin or a Chrome extension like MetaMask. It's a huge advance. Something I should mention at this stage as well, the system very cleverly anonymizes you. So you could have one II, Internet Identity Anchor, that you use for many different dApps. But when you authenticate to these different dApps, they each see a different pseudonym. So there's no way that somebody who owns multiple dApps, say, or is involved in multiple dApps, or some kind of advertising program, can track your usage across these different dApps. So it's a very powerful system, as well as something that's very easy to use. And we believe it moves the game on both from username password pairs and from traditional blockchain authentication methods. It gives you not only an improvement in usability and reduced friction, because now you don't have to remember usernames and passwords. You just have to have a bunch of devices associated with your II, so you can look at your phone or press the fingerprint sensor. But you get even better security than you do with traditional blockchain authentication, cryptographic authentication systems. Okay, so this has been going very well, and the reason I'm going to show you this clip is we just passed 725,000 IIs created in just 4 months since launch, which just reflects this enormous growth we're seeing in the number of developers building on the internet computer, the number of smart contracts being uploaded and hosted, the number of dApps, and the number of active users. And if you're wanting to have a go of internet identity, I recommend, for example, you try OpenChat. Just go to oc.app, oc.app, and that will redirect you to a UI on the internet computer, and you can use, you create an internet identity to use that. If you fancy using a chat system that runs entirely off blockchain, which of course is revolutionary. Imagine smart contracts actually processing chat messages. Pretty cool. Okay, so when we first launched, we underwent Genesis 10th of May this year, 4 months ago. We only really supported these really super convenient devices like the fingerprint sensor on a Mac, if you're on Windows, you had to use other systems. So Windows has its own sort of biometric framework called Windows Hello. And, modern Windows laptops have fingerprint sensors and do facial recognition and things like that. So, we have extended Windows Identity so that it works with that Windows Hello system. And that's one of the reasons why. We saw immediately that we supported Windows Hello, we saw a huge acceleration in the number of Windows Internet Identity handles, anchors being created, and it's no wonder. There's like 1 billion users of Windows Hello. I think 825 million or something worldwide. So, and a lot of people, are using Windows laptops. Arguably, in recent times, Windows has been fixing a lot of their legacy problems, and it's a much better platform than it used to be. Look, so anyway, to celebrate this incredible growth and the technical triumph that is internet identity, which is an enormous credit to everyone working at DFINITY Foundation, that really moves the blockchain game forward. We're going to go back a few weeks and show you this old clip from a guy called Christoph, who's demoing how he first got internet identity working with Windows Hello. He's actually going to start off as well, which is really nice, talking a little bit about some of the cryptography involved, because some of the there are a lot of cryptographers that work at the DFINITY Foundation. We certainly employ far more cryptographers than any other organ in blockchain, but arguably we probably employ more cryptographers or more leading cryptographers than any other organization in the world, other than perhaps the NSA or something. But no one knows who they employ. They're all there, and there's a lot of very technical people, obviously, attending, global R&D at DFINITY. But some, not everyone. A lot of people in operations too, working on things like community outreach and things like that. So Christoph kind of gives a sort of high-level overview of how internet identity works and the public key cryptography behind it, which patches through to the chain key cryptography framework, which makes the revolutionary internet computer possible. So, without further ado, over to Christoph. Let's watch the clip.
Please go ahead. Yeah, thank you.
Okay, so my plan for today is to demo. I need to move Zoom out of the way. Is to demo Windows Hello for internet identity, but that demo takes about 1 minute and it's kind of boring. So what I'm going to do is something else. So people, when they describe object-oriented programming, what they often say is, if you want to create a banana, you first have to instantiate the gorilla to hold the banana. What I'm going to do is, if Windows Hello is the banana, I'm going to show you the jungle. And so my plan is to show you how internet identity works kind of as a whole from the perspective of a non-cryptographer. And then hopefully have enough context for you that I can show you where in the whole picture Windows Hello and the change we made to enable RSA signatures comes into play. So I'm going to try this more experimental way of doing this demo. So step one, I'm going to do a quick disclaimer. I'm not a cryptographer, which means that I'll simplify and gloss over details a whole bunch. Simplifications are not just because I don't know, they're also because it makes it easier to understand what's going on. If at any point you have a question, please just ask. My goal is to have others understand how this works, not to show off that I understand it. And if I run out of time in the sense that I only have 1 minute left, please let me know so that I can do the demo, because I want to do the demo, but it's kind of boring and I'm just going to do it at the end. Okay. Cool. So step one, I'm going to introduce you to public key cryptography. So public key cryptography is kind of what is underlying basically all security going on the internet. And it's a very vital and fundamental idea the IC relies on. So the idea of public key cryptography, and it's kind of a misnomer because it's not just about public keys, it's about public and private keys, and these form a so-called key pair. And for every public key, there is exactly one private key. I will be color coding these in yellow and red. So red is private, yellow is public. And you might have heard that term before. On the internet computer, we sometimes call public keys principals. That is a simplification, but it works for the purpose of this demonstration. Are there any questions about that part? Right, I can't look at the chat, so if you actually have a question, please speak up. So what can we do with this public key cryptography? So the operation we're interested in for internet identity is that we can use them to do what's called signing. So on the left here, we have Alice, and Alice has her red private key, right? She keeps that one private to herself, and her public key she can share with others. And Bob holds Alice's public key. And so what Alice wants to do is she wants to send the message M to Bob. And what Alice does is that she creates a signature. And this part means that she uses her private key to create a signature for the message M. And then Bob can use the public key of Alice, the corresponding public key, to verify the signature on this document. So when Alice signs this document with her private key, Bob can verify the signature. And when this verification works out, succeeds, Bob has these two guarantees. So he knows that this signature definitely came from Alice, because Alice is the only person holding this private key. So he can be sure that this signature came from Alice, and Alice signed exactly the document M that Bob has received. Okay, and so these two guarantees that Bob gets from verifying that signature are very important. Okay, and when you look at the internet computer, what is actually happening, every message someone sends to the internet computer passes along a principal, and that principal, as we know, is a public key, and it also contains and alongside the message, when you call the internet computer, you pass along a signature that verifies that exactly you were the one that sent that message, and it also verifies that you sent exactly the message the internet computer is looking at. Okay, and this happens before a canister gets access to that request. So the internet computer or the replica actually will do this verification. And by the time that you as a canister author see the principal of a caller, it has verified that exactly that principal corresponds to the message that has been sent. Are there any questions about that part? Great. So unfortunately, that's not quite enough. So we're going to have to kick up the abstraction level one more notch here to understand how internet identity works. So what we're going to talk about now, using this signing capability that we've talked about. So using public key cryptography, if we can do the signing stuff. And what we're going to talk about is what's called a delegation. And the idea here is that the abstract idea is that we have kind of transitive trust. Okay, so now we don't just have Alice and Bob, we have Bob, Alice, and Charlie. So A, B, and C. And the goal here is that C wants to send a message M to B. Okay, but B only trusts A and A trusts C. Okay, and so what we can do with the delegation is kind of like extend this trust, like follow this trust chain and build a trust between B and C. So how this works is that C asks A, because A trusts C, C asks A to sign its public key. Okay, so C asks A to sign the public key of C using A's private key. And what this gives us is what I'll call DAC. So the idea here is that we have a delegation that assigns that assigns like trust from A to C essentially. And then when C gets these DAC back, it signs the message M it wants to send to B in the first place with its own private key. Okay. And it attaches the delegation it has gotten before. Okay. And so now what B gets is M signed with the private key of C and this delegation. And then B goes ahead and verifies the delegation DAC using the public key of A. It knows, right? So it trusts A, so it knows the public key of A. When it has verified the signature, what does it know? It knows it was exactly A that signed, was exactly A that signed this delegation. And it knows that the message inside, which is the public key of C, is exactly what A signed, which means that now it has the public key of C, and it can now verify M with the public key of C that it has just received. Okay, and so this way now we have this trust extended here basically, right? So B now trusts C, even though it only trusted A and A trusted C. That's the most complicated mathy thing we're going to do. Does that make sense, or any questions here? All right, great. I think I'm probably running low on time, but let's see how internet identity works. We're going to need all of the things we talked about before. Okay, so this is internet identity. We've got three parties here. We've got Mallory, which is a good friend of mine. Cryptographers have been slandering her for years, but that stops now. And Mallory has two devices. She's got a YubiKey, which has a private key Y and a principal or a public key Y, and a laptop, which has a private key L and a public key or a principal L. There's the open chat canister, and here's the II canister, the internet identity canister. And what the open chat canister wants is it wants a stable principal that it can associate Mallory with. Okay, but that principal can't be the principal of this YubiKey or this laptop, because Mallory might lose these devices, or she might want to use both of these to sign into OpenChat. So it can't be either one of those. So that's where internet identity comes in, and it generates a principal which is stable, and we're going to call this PM, right? This is the principal for Mallory. And PM is generated by the internet identity, and it is generated using these two inputs. So I'm going to call this function IIGen. So the inputs to this PM are Mallory's anchor, identity anchor that she's used here, and the URL of OpenChat. Okay, and this is where the thing happens, where every app uses this, gets a different pseudonym or different principal for Mallory. And the OC, so OpenChat, trusts the internet identity. Why does it trust internet identity? Because it runs on the NNS subnet. And if it doesn't trust the NNS subnet, if OpenChat wouldn't trust the NNS, then it basically, there would be no point running on the internet computer because it could be deinstalled at any point in time. Okay. But what's the private key that corresponds to PM, right? And that is actually, this private key is, I'm going to call this one P. This is the subnet. This is where the chain key technology bit comes in, right? This is the private key that is held by the subnet that II is running on. Okay. I said every public key has exactly, every public key has exactly one private key it corresponds to. In our world, it's a bit, in the other direction, it's not the same. So this private key that is held by the subnet can actually generate a bunch of different public keys, and they're generated this way. Okay, so let's keep going. So if you compare this to the diagram we had before, we have this trust line. We do need this trust line still. So how does the internet identity trust Mallory? Okay, this is the line we want to draw. And the way this works is that internet identity stores for every identity anchor, it stores the corresponding public keys. Okay, so it stores PY and PL together with the identity anchor. And so what internet identity then does is that it can ask Mallory to use either of these devices to establish the trust that is actually Mallory calling out the internet identity here. Okay. And so the last thing we now need is we want to do this delegation thing we did before, but what key are we signing, right? Remember, we needed a public key for Mallory and we needed a key for the internet identity. Well, what we're signing here, Mallory actually, the OpenChat frontend or Mallory herself generates a new public key. It's called a session key. That's why I'm going to call it PS, and stores the corresponding private key in her browser. Okay, so and then what we're going to do is Mallory asks the internet identity to sign this session key, right? So Mallory asks II to sign PS, right? So the internet identity signs this public key. Okay, and this gives her back a delegation, which I'm going to call DSM because it delegates from, no, the wrong way around. I'm going to call it DMS because it delegates from PM to PS. Okay. And now Mallory can use her private key, this private key, to sign messages she wants to OpenChat and attach this delegation. And OpenChat can verify that Mallory has the permission to sign against the principal or the public key PM that she, because she has a delegation that tells her, that says that internet identity trusts her to be able to sign for this principal. I think that's that. Any questions? I know that this is a bit convoluted, but hopefully we could see the different concepts tying together and showing how this works out.
Oh, does OpenChat, after Mallory signs into II, does OpenChat have to talk to II every time it wants to verify a message?
No, and that's, no. And exactly, great question. So this is exactly what this delegation thing, this is exactly why we have the session key, which is generated in the browser store and held, and it's valid for a specifiable amount of time. This delegation, like Mallory requests this delegation from II, and this delegation says that II trusts Mallory's public key. And this is why, because Mallory holds the corresponding private key, Mallory can keep talking to OpenChat, and OpenChat can be sure that II has trusted Mallory's public key. Does that make sense?
Thanks.
Great, cool. So now, where does Windows Hello come in? It's here. Windows Hello is just another one of these devices, and it generates a private key. But Windows private keys, so Windows Hello private keys use a different signature scheme than the ones YubiKeys use. And so the trust between internet identity and Mallory couldn't be established yet because the replica didn't know how to verify these signatures. Now we've made that change, or the crypto team was so kind to make that change in the replica that we can now verify these signatures. And so now I'm going to stop sharing on this screen and move over to this machine, hoping that you can see this. Okay, and I have this very tiny demo. So this is a, and I hope you can still hear me. So this is a tiny little test app we built on the testnet we're using here. So I can click this button. It's going to redirect me to an internet identity instance that is running on this testnet. And we're going to deploy this soonish because we have kind of finished the testing and it seems to work. And now what happens is I have already created one here, but what I can do now is I can say authenticate. And as you can see, this is now the dialog for Windows Hello, and it has recognized my face. And I can say, okay, I'd like to continue. And as you can see, I can now proceed back to the little test app we built. And if it shows me a long principal over here, this is now the public key that internet identity has dealt for my anchor and URL combination. Great. I hope I wasn't too over time.
No, that was perfect. Thank you very much, Christoph. That was very nice background and a cool demo. Any questions for Christoph?
You said something that surprised me. I assumed that the obstacle for adding devices like Windows Hello or whatever was the way they had like some browser web authentic compatibility, but it seems to be the scheme for signing. So that's the main blocker to adding devices, or is combination still both? It's still browser web authentic and then also the scheme.
It's both. So the macOS devices use ECDSA for signing, which is the algorithm we already supported. But Windows Hello uses the RSA scheme, but we're not aware of devices we'd want to support that use other schemes so far. Okay. So at this point, it's mostly device compatibility with web authentication. Exactly. Yes. But yeah, I think unlocking all the Windows users out there is a pretty large chunk of users that will now be able to access internet identity without having to buy a security key.
So what happens if II is if Mallory's identity is compromised? Someone stole her device and manages to log in. She tries to revoke her identity and stuff, but that session that the other person has will just stay open, right?
Yes, so the session the other person has will stay open for a while. It's a session for OpenChat though, right? It's not the session for II. So it can't be used to recreate, like to re-add devices. It can just be used to keep chatting on OpenChat.
Okay.
I have a question too. I always assume that internet identity is a single canister on the NNS subnet, but is that true?
It is, yes, it is right now. We're hoping to move it to an app subnet sometime soon. Right now it's on the NNS subnet. But yes, it's a single canister. Exactly.
Thank you.
Any last question for Christoph?
What's the trade-off?
Go ahead.
What's the trade-off of NNS versus app subnet for the II canister?
Well, you need to trust one more subnet because, well, trusting the NNS subnet is kind of a given because trusting the NNS subnet means trusting the NNS. If you move it away, you don't want II to just be a canister controlled by a person, right? So you do need a service network system kind of thing. If you want to run II as it's on an app subnet, right now it can reuse the NNS as its like voting mechanism of upgrade. So you have to build that. So that's one of the trade-offs we have to make there basically.
I have a question. How long is the session valid? The private key stored in the browser?
So the maximum is 8 days, but you can set like you can, when you redirect to II, you can pass along the time to live you'd like for that.
So it's up to
that
the user to
delegation.
decide. Okay.
It's up for the app actually. Like OpenChat sets it, but
Okay. Thank you.
Awesome. Thank you very much, Christoph. And thanks to all the other speakers. We're exactly at time, so let's end here. And yeah, see you all next week.
So there we have it. Windows Hello support, incredibly important. Looking forward to us passing 1 million eyes. Of course, at some point, this is going to go, the growth's going to go far, far faster than it is now. Within a couple of months, hopefully, I'm not sure, we're introducing service nervous system functionality, which is essentially going to allow dApps to assign control to their own network nervous system and get their own governance token ledger. So, dApp's going to get their own NNS front-end dApp and their own version of the ICP ledger. Once they do that, they're going to become fully autonomous, and they're going to start giving governance tokens to users. For example, you can imagine a user in a blockchain social network dApp running off the internet computer. If they have a good social graph, might get some governance tokens, or more governance tokens if they participate in helping with things like moderation. When that happens, we're going to see this just go to the moon. That's coming, but hopefully we can even get to 1 million internet identities created before then. And then, let's just make sure we finish this year with the internet computer having more active users than any other blockchain in the world. Hopefully, more active users than all the other leading blockchains put together. That's what we want. Okay, thanks guys. See you next episode.